Alright class, welcome to this lesson on logarithmic functions. So we're going to introduce a new type of function that you may or may not have seen before. Our goal for this lesson is to be able to evaluate logarithmic functions and also graph them, just like we did with exponential functions. Alright, so those are the goals for today. So for the first problem, what we want to do is we want to introduce the idea of logarithmic functions by starting with an example. Okay, so in this example, you want to solve for x in the following exponential equation. In order to solve for x here, well, we know we had to figure out, well, 10 to the what power gives you 100. In that case, if you're pretty decent with your exponents, then you would know that this would equal 2. 10 to the second is 100, because 10 times 10 is 100. So it's a very easy exponential equation to solve. Now if we look at part B, 10 to the what power gives you 1,000. Well, we know there's 3 zeros in there. 10 times 10 times 10 is 100, so I know that 10 to the third will give me 1,000, which means that x is 3. For part C, 2 to the what power gives you 8. We've done this a few times. We know that 2 cubed is 8, because 2 times 2 times 2 is 8. So that means x is equal to 3 here. For part D, 3 to what power gives you 1? So remember that anything to the 0 power gives you 1. It doesn't matter if it's a million to the 0 power, it will always give you 1. The only number that doesn't really work out for is like 0 to the 0 power, but everything else works out where you get 1. So we know that 3 to the 0 power is 1, so x has to be 0. Alright, so far, if you're okay with your exponents, this should be pretty straightforward. But now let's look at part E. It's saying 10 to the x is 155. So at this point, you may be having a bunch of question marks. What number can this be? You know, it can't be 2, because that would be 100, and it can't be 3, because that would be 1,000. So we know that this exponent is between 2 and 3. And it's actually going to be a decimal of some sort. How do we find that decimal? Well, this is where logs come into play. So logs help you retrieve exponents from an exponential equation. So a logarithm helps you find a missing exponent or power. The logarithm of y with base b is denoted by this symbol. So this is the notation that we're going to be using. And the way you read this is you read this as log base b of y. So that's read as log base b of y. So if I had, for example, this symbol, right, then this would be read as log base 2 of 5. Pretty simple, right? Now the reason, so 2 is the base, right? So that's why we call it base 2. So this is the base in the expression. And then 5, 5 is what you want the log to equal to. So we'll talk about that more in a little bit. So in essence, there are two forms. There's a logarithmic form, which is the one that we kind of just wrote down. So it's log base b of y equals x. So that's the log form. The exponential form is b to the x equals y. So how do you convert between the two forms? Well, there's a couple ways that you can convert between them. So we know that it's called log base b for a reason. So b is our base, right? And a log gives you an exponent. So a log will always be equal to an exponent, which is why x is my exponent. And then by default, it's equal to whatever is inside the log, which is the y. So you have to be able to convert between the two forms. We're going to do a couple examples on that. Think of the logarithmic function as the opposite. Okay, so you know that in math we always have opposite things, right? We have plus and addition and subtraction, multiplication and division. We have squaring and square rooting. But this time we have exponential functions and logarithmic functions. So logarithmic functions are the opposite or the inverse of the exponential function. So therefore it cancels out or undoes the exponential function. So knowing this idea that they're inverses or opposites will actually help you out a lot in the long run, because you'll be able to solve easier in having this concept in mind. So I'll show you an example. So let's say we want to rewrite the logarithmic equation into an exponential form. So we want to convert between two forms. So right now this is in log form. So there's a couple ways you can do this. The way I'm going to show you is I'm going to show you by canceling out. So we know that the log has a base of 3. So the only way we can, and remember that we also know that the log cancels out exponential. So what I'm going to do is take that log base 3, and I'm going to raise both sides to the third power. So I'm going to raise both sides to the third power. And what this does, remember that we said that exponential functions and logarithmic functions cancel. So this can be rewritten as 3 to the log base 3 of 9 equals 3 to the second power. So we're essentially raising both sides of the equation to the exponent slot with a base of 3. And that's how you cancel out logs. So this now will cancel out with this log because they're opposites or inverses of each other. And now you're left with 9 equals 3 squared. So we're left with 9 equals 3 to the second. And notice that follows the form b to the x equals y, right? So this is of the form, that's your b, this is your x, and that's your y. 9 is y. And that's an exponential form. That's all you have to do. Just convert it to that form. So we're going to do the same thing here, okay? So we're going to do 8 raised to both sides, because the base here is 8, log base 8 of 1. So 8 raised to that side, 8 raised to the 0 power. So therefore the logs cancel out, but I'll show you how it looks like, so that you can see what we're doing. So we're raising 8 to both sides of the equation. So those cancel. So you got 1 equals 8 to the 0. And that's it for that one. Same thing going on here. So the base is 5. So this is log base 5 of 1 over 25. So we're going to do 5 raised to both sides. And that's the only way that we can cancel out that log. So now we have 1 over 25 equals 5 raised to the negative 2 power. Alright, so it's important to know that the log retrieves the exponent. So when I convert this to a log form, notice that it retrieves the exponent. It's equal to the exponent. So the log is equal to the exponent because it's trying to retrieve it. So if you notice, it's always equal to that exponent in all cases. So what's the log of 1? Well, the log of 1 based off of example B is always 0. Because anything to the 0 power is 1. Alright, so now let's look at number 3. This wants you to evaluate the expression without a calculator. So we're going to be converting it to the exponential form and then essentially solving it that way. Okay? So what we're going to do is we're going to set this equal to a variable. Alright, so I'm going to set it equal to, x. Alright? And I got to figure out what x is. So I'm going to convert this to the exponential form. So I know that I'm going to raise 4 to both sides. 4 to both sides. Because there's a base of 4 here. So now they cancel. So I have 64 equals 4 to the x power. Alright, so at this point you just got to figure out 4 raised to what power is 64. Well, we know that 4 times 4 is 16, right? And then if you were timesing it by another 4, you would get 64. So that means I multiplied it by itself 3 times to get to 64. So that means my x is equal to 3. which means that the log base 4 of 64 equals 3. All right, so both of those suffice. All right, let's do the same thing here. So we have log base 2 of 1 over 8, so set it equal to x, and then cancel out the log by raising both sides to the base, which is 2. So we have 1 over 8 equals 2 to the x power. Okay, how do we figure this out? Well, remember, you can rewrite this 1 over 8 as 8 to the negative 1 power, right? So this is a fraction, which means that you can flip this, right? So we know that x could be a negative number. So what I'm going to do is I'm going to rewrite the 1 over 8 as 8 to the negative 1 power. Okay, so I'm going to rewrite the 1 over 8 as 8 to the negative 1 power. This is where knowing your negative exponents help you. Remember that the negative exponent means you flip and forget. So that means you're going to flip it to 1 over 8. So I haven't done anything new. I just went backwards, right? Now 2 to the what power will give you 8. So what I do is I know that 2 times 2 times 2 is 8. So this is really 2 to the third. All right, so 2 to the third is 8. 2 times 2 times 2 is 8. Now we multiply those exponents, so that it gives you 2 to the negative third power equals 2 to the x. And now you can tell that x is equal to negative 3 just by looking at it. So x is equal to negative 3. So that means that the log is equal to negative 3. All right, so now let's do this one. We're going to set it equal to x. Since the base is 32, I'm going to do 32 raised to both sides. So I have 32 to the x power equals, or we'll cancel that out first. So this will cancel out. So we got 2 equals 32 to the x power. All right, so how do I do this guy then? Well, for this example, what you can do is rewrite 32 in terms of 2. So I know that 32 is 2 times 2 times 2 times 2 times 2. 2 times 2 is 4. 2 times 2 is 4. So we got 4 times 4 is 16. 16 times 2 is 32. So this is the same thing as 2 to the 5th power. So I'm going to rewrite this as 2 to the 5th power. And then don't forget that x there, so I'm going to put that x right there and multiply it. 5 times x. So the 32 is 2 to the 5th, and then the x is just hanging out there. All right, so then what's the power for this 2 on the left side? It's just 1. Right? So that means that we're going to set 5x equal to 1. So 5x equals 1. Divide both sides by 5. X is equal to 1/5. So basically, if you took the 5th root of 32, remember the reason why I say it's 5th root is because remember that 32 to the 1/5 power is power over index. So power is 1, index is 5. And if you did the 5th root of 32, you should get 2. All right, the last one. So we're going to set this equal to x. So we're going to raise both sides to the 10. So the log and the 10 cancel. So we got 1 over 10 equals 10 to the x power. Again, since this is a fraction, flip it up and then make the exponent negative. And now you can clearly see what the exponent is. The exponent is negative 1. Okay, it takes a little bit of practice. And you have to know your exponent properties because this is where it comes back to, to get you if you don't know them. All right, so that's without a calculator. There's going to be problems where you do have to use a calculator, and I'll show you where the log key is for that. All right. So there are a couple special types of logarithms that we'll consider in this class. All right. There is the common logarithm. The common logarithm has a base of 10, and since the common logarithm is so common, instead of just writing it as log base 10 right here, we usually just write it as log. Okay, so when we just write log, we assume that it's log base 10. So like if I wrote log of 5, then we assume that it's log base 10 of 5. So we don't write the 10. Okay, it's usually invisible. So when you see log 5, just think base 10. The other type of log is the natural log. And this is a logarithm with a natural base e. Remember the natural base e? We talked about that in the last lesson. So this is where it's going to come back. So instead of writing it as log base e, we use ln. And ln stands for Logarithmus Naturalis, or natural log. It's just in another language. So when I write log base, I'm not going to write it as log base e. I'll just write it as ln of like 2 or something. And that's to be assumed that this is log base e. All right? So just keep that in mind. We're not going to write it as log base e. We're going to write it as ln. And we're not going to write log base 10. We're going to write it as log. So they want you to evaluate this expression using a calculator. So, and round to 3 decimal places. So this is where we're going to use our calculator. Remember that this log really means log base 10. Okay? But we just don't write it generally. So we're just going to plug this on the calculator. So I'm going to show you where it is. So if you look in the TI-30, this is the one that we usually use in class. So if we look in this calculator, you'll see that there is a log key. All right. It's kind of hard to see that here. I'll circle it right there. So there's the log key. So you're literally going to type the log and then whatever the number. So you're going to type log and then 7 and then parentheses, and that's it. And then there is a dedicated ln key as well right there. Okay, so those are the 2 keys that we'll be using in this class for this lesson. All right, so if you were to do log base 10 of 7, then, so let's see what we get here. Log base 10 of 7, or common log of 7, you're just going to get 0.845. We're going to round it to 3 decimals. All right, and then we're going to type in the ln using the ln key that I showed you. And we got 3.219. Remember that this is the same thing as log base e of 0.25. So really what you're doing when you do this, you're trying to figure out e to the what power gives you 0.25. So if you were to like solve this, right? You're going to raise both sides to the e so you can cancel out the log e. And then you have 0.25 equals e to the what power. So e to the what power gives you 0.25. Turns out the answer is, excuse me, turns out the answer is, let me make sure here, e to the, let me double check that number. I think that number is too big. Let me double check. Ah, there you go. Okay, so that number is too big. Sorry, guys. Let me erase that. It was too big of a number. It has to be negative. So negative 1.386. Okay, sorry about that, guys. So negative 1.386. So e to the negative 1.386 will give you 0.25. That's what it's trying to tell you. So e to the negative 1.386 will approximately be 0.25. So the log is retrieving what that exponent is. As mentioned before, logarithmic functions are inverses of exponential functions. Therefore, they cancel each other. And this is what we were talking about earlier, right? So to cancel out the log base b here, you're going to have to raise both sides to the x power. So we're raising we're going to raise both sides, or raise b to both sides, right, to cancel each other out. And similarly, if we had, and that's why this cancels out right here, if you notice, log base b and b cancel out, and which gives you x. All right, so that's basically how you cancel each other, by using those operations. And similarly, remember that ln is log base e. So that means log base e and e also cancel each other out, which is what we were talking about earlier. So therefore, if you were to do ln of e, they would cancel out and give you 1. If you were to do ln of e squared, they cancel out and give you 2. How do they cancel? Well, let me show you. So ln of e equals 1. So let me use I'm going to use the cursive L so that we know it's ln. Okay. So now ln is the same thing as log base e, and then we have e here. So you're going to raise both sides to the e to cancel this out. So you have e equals e to the first power. So you see that if 1 is the first power, this is a true statement. You see that e to the first power is e. So therefore, ln of e has to be 1, otherwise this wouldn't be true. And for the other guy, so just to kind of show you, what's ln of e squared? So we're going to set it equal to x. So we're going to raise e to both sides so that those cancel. So e squared equals e to the x. So what does x have to be? 2. So that's how we get 2 there. So basically, you can think of them as canceling out and giving you 2 at the very end. So you can think of the ln and e as canceling out. And that's what I'm going to be doing in the future. All right, so simplify the expression. All right, so now notice that this log has an divisible base 10. So this is 10 to the log base 10 of 8. So that means these cancel each other out, leaving you with 8. And that's how simple it is. All right, so now we have log base 3 of 9 to the x power. So what we're going to do is we're basically going to, I'm going to show you, there's a couple ways that you can do this. So the first way is, well, I know that 9 can be rewritten as 3 to the second power, and I have an x hanging out there. Remember that x is there? So I have 3 to the second power times x. And then now I know that these cancel each other out. You see that the logs are the same here, the log and the 3? So those can cancel out, and that gives me 2x. And that's what this property is saying here. So this is based off of this property, the fact that the b and this b can cancel each other out, leaving you with x. Okay, so these are just some properties that help you out tremendously, save you a whole bunch of time. So now let's do this one. So I have log base 5 of 125 to the x. Well, I know that 125 is 5 raised to the third power. 5 times 5 times 5 gives you 125. And then don't forget the x power there, right? So now notice that the 5 and the log base 5 cancel, leaving you with 3x. And then for this guy, we have log base e. Remember, ln is log base e, and then we have e to the third power. So since these are the same, they cancel each other out, leaving you with 3. All right, so these are just shortcuts to get straight to the answer. All right, now we're going to go back a little bit into the previous unit, and we're going to talk about inverses. So remember, we talked about the log is the inverse of the exponential function. So in order to find the inverse, remember, you swap x and y and then solve for the new y. And then, of course, you're going to convert that to f inverse of x, right? So we're going to use this to find the inverse of the logarithmic function, and then you'll see that we're going to end up with an exponential. So let's go ahead and find the inverse of the log. So again, swap x and y here. All right, since we have a log base 8, I need to cancel that out. So in order to cancel that out, I'm going to raise both sides to the 8 power, or we're going to do 8 raised to both sides. And that will cancel these out. Remember, that cancels out because of this property right here. See, if I have 8 raised to the log base 8, it'll cancel out, leave me with x. So that's the property that we're using, the fact that they're inverses. So these cancel. So now I have y equals 8 to the x. Y equals, I'm going to just write the y there, and I'm going to write this down over here. Y equals 8 to the x. All right, and then therefore, now I'm going to replace y with f inverse. All right, and there's my inverse function. Notice that I get an exponential function. I get something raised to the x power. This is exponential. All right, now let's do it for this one. So we have y equals, I'm going to rewrite ln as log base e, just to show you. And then I'm going to get rid of that log base e by raising e to both sides, because the base is e. So now these cancel each other out. So you have e to the y. Oh, I forgot to swap x and y. Sorry, guys. So let's do that first. So swap x and y, change that up real quick, and then we solve. All right, so now I got e to the x equals y minus 3. And now we can solve for y by adding 3 to both sides. So we have y equals e to the x plus 3, and then replace that with f inverse. All right, so notice that e is the inverse of ln, and 8 to the x power is an inverse of log base 8. So they're all inverses of each other. All right, now we're going to look at the graphing, which is the last part of the lesson that we're talking about. So in order to graph logs, we're going to do the similar procedure to what we did with exponentials, but what we're going to do is, first of all, let's rewrite this as log base 10 of x. So that way we remember that common log is just log base 10. All right, so we need to find good numbers for x, all right? So what are some good numbers? Well, for example, I know that, so let's rewrite this in exponential form. Maybe that'll help us out, help explain why. So we're going to rewrite this as an exponential. So I have log base 10 of x equals y, right? So I'm going to do 10 raised to both sides. And that cancels. So we have x is equal to 10 to the y. All right, so what this is saying is that we have to choose x's that are nice, right? So like if x were to be 10, right, then I have 10 equals 10 to the y. Well, I know that 10 to the first is 10, right? So this will be a nice number to choose. I do not want to choose something like 5, because if I chose x was 5, well, what exponent will give me 5? There's no, this is going to be a decimal, so this is not a nice number to choose. 1 is also a nice number because 10 to the 0 power is 1. Okay? And similarly, if I did 1 over 10, well, 10 to the what power gives me 1 over 10? It's going to be 10 to the negative 1 power. All right? So what I think would be helpful for you is write it in this form, and then choose the value of y. Okay, so choose the value of y. So let me just kind of rewrite this over here, down here, and we're going to choose the value for y. So let's choose some negative values for y and some positive values for y. So -2, -1, 0, 1, 2. All right, normally we choose values for x, right? But since I put it in this form, it's easier to choose values for y and then figure out what x is. So if I were to plug in -2 for y, well, what's 10 to the -2 power? Well, remember, flip and forget, right? So this flips as 1 over 10 to the second power, and 10 to the second power is 100. So this is 1 over 100. All right, so now if x equals 10 to the -1 power, 10 to the negative 1 power is 1 over 10. What about 0? Well, I know 10 to the 0 power is 1. And then if I did 10 to the first power, that's 1. 10 to the, it's 10. And then 10 to the second power is 100. So you see how I kind of did that? I kind of rewrote it as this, 10x equals 10 to the y, and then pick the y, and then I can get the x from it. All right, so now we're going to say when x is 1 over 100, which is very small, by the way, y is negative 2. So I'm going to zoom in on this graph. And when x is 1 over 10, which is also very small, y is negative 1. When x is 1, y is 0. When x is 10, y is 1. All right, so this graph looks like this. It's increasing. It doesn't look like it's increasing, but it's increasing. This is showing an increase. And then notice that there is an asymptote here. It's trying to approach the y-axis. It's trying to approach the y-axis, but never actually reach it. So we do have an asymptote here. We actually have a vertical asymptote. So we have a vertical asymptote at x equals 0, which is there, okay, which is the y-axis. All right, so, and does this have an x-axis? Or does this have an x-intercept? Well, yeah, it does have an x-intercept. The x-intercept is here. So it's at 1, 0. So x is equal to 1. Does it have a y-intercept? Well, we know it never crosses the y-axis because of the vertical asymptote. So there is none here. Does it have an asymptote? Well, we just said that it has a vertical asymptote at x equals 0. Domain, what is the domain? Well, this graph is valid everywhere except for, so this graph, notice that it's only on the right side of the coordinate plane. So we have no negative x values. We cannot plug in any of these negative values into the function. We can't plug any of them at all. We can't even plug in 0 because 0 is an asymptote. So that means x has to be strictly greater than 0. It can't even be equal to 0 in this example. All right, and then what about our intervals for this function? Well, this is increasing, we know that, since it's going up, and it's increasing in this example, it's increasing from 0 to infinity. So it's increasing from 0 to infinity. So it's increasing basically for positive numbers is what it's saying. All right. What about the range? Well, the range is all real numbers since we have all the negative values for y and we have all the positive values for y since it's increasing from bottom to top. So the range is all real numbers. All right. And then the end behavior is, so the end behavior is as x goes to the right. What does the graph do? As x goes to the right, well then y is increasing. Although it's increasing slowly, it's still increasing, and it's increasing to infinity. Y approaches infinity. So this will continue to increase. And then as x approaches, so in this case, the end behavior for this, x is not approaching, x cannot be negative infinity, right? So as x approaches, so what we're going to do in this example is as x approaches 0, what happens? All right, so in this example, there is no negative infinity, right? We're not going in this direction. We're only approaching, we're not going in the negatives, we're approaching 0 in this example. So as x approaches 0, what happens to the graph? Well, y is approaching negative infinity. Okay, so this one's a little tricky because of this asymptote here. It can't be negative. All right, let's do another example. All right, so let's graph part B. So the way I'm going to show you is I'm going to convert it to an exponential function. So remember with the exponential functions, we set the exponent equal to -2, -1, 0, 1, 2. We're going to kind of do the same thing here, but first we got to convert this to an exponential function before we even do anything. So to convert this to an exponential function, I'm going to get rid of that 4. So I'm going to subtract 4 on both sides. Okay, so I'm going to rewrite the function over here so that I can show you the process. So what I'm going to do is I'm going to subtract the 4 on both sides to get rid of it. So now I'm left with y minus 4 equals log base 1/2 x plus 1. Now to get rid of the 1/2, I need to raise both sides to the 1/2 power. And that will get rid of that. So now I have 1/2 to the y minus 4th power equals x plus 1. Okay, so now it's sort of in the exponential form now, as you can see. All right, I'm going to go ahead and subtract the 1 as well. I'm going to subtract the 1 over just to get rid of it so we can solve here. So we have x equals 1/2 to the y minus 4 power minus 1. Okay? And now it's in exponential form because it has a base raised to a power and then stuff in that power. Okay, so this is an exponential function. Now what I can do is I'm going to make the exponent equal to -2, -1, 0, 1, 2. So I'm going to make this exponent equal to that exponent right there. So I'm going to set that exponent equal to -2, -1, and so on, 0, 1, and 2. So basically I'm setting the y equal to those instead of the x. Why am I setting the y equal to it? Well, remember that the log is the inverse of the exponential function. So when we made the exponential function, those 5 numbers, it'll reverse or flip to the y because we're talking about an inverse now. So it flips to the opposite direction. So now we're dealing with the y as opposed to the x. So now we got to get rid of the 4 here, so I'm going to add 4 to both sides. All right, and this will give me y equals 2, which makes sense because 2 minus 4 is -2. So y can be 2. -1 plus 4 is 3, and we can see there's a pattern here. It's going by ones, and we can continue that pattern. All right, now that we got the y's, we can plug in to get x. So we're going to plug it in, the y's in there. So we have x equals 1/2 raised to the 2 minus 4 power minus 1. And then you can do this on the calculator. 1/2, this will be 1/2 to the -2 minus 1. Remember, flip and forget. So this will be 2 squared, which is 4. 4 minus 1 is 3. Okay, and you can do that on the calculator if you have trouble with that. Although at this point you should be practicing this so that you don't have that issue. All right, now let's do let's plug in y equals to 1. So when we have that, we got x equals, let's do it over here. So we have to make sure we have plenty of room. All right, so we got x equals 1/2 to the 3 minus 4 power minus 1. We're plugging in 3 into y. So now we have 1/2 to the -1 minus 1. this flips, becomes 2. 2 minus 1 is 1. Right? So now let's do the next one. Let's plug in y is 4. So we got 4 minus 4. Power minus 1. 1/2 to the 0 power is 1. 1 minus 1 is 0. So x is 0 here. Now let's do 1/2 raised to the 5 for y. So we have 1/2 to the 1 power minus 1, which is negative 1/2. Alright, now let's plug in 6 for y. So we have 1/2 to the 2nd power minus 1. 1/2 to the 2nd power is 1/4. 1/4 minus 1 is negative 3/4. Alright, so now we can graph the function, graph the points. So we have 3, 2, 1, 3, 0 and 4, negative 1/2 and 5, negative 3/4, and 6. Alright, so notice that this graph is continuously decreasing, and it's approaching, looks like it's approaching this vertical asymptote here. So it's approaching a vertical asymptote of, so vertical asymptote at x equals negative 1. Okay? And the way you can tell is this guy will kind of tell you what the vertical asymptote is. It's going to be the opposite of the plus 1, so it's going to be negative 1. Or you can set that equal to 0 and solve. If you solve that, you get x equals negative 1. So that's another way that you can tell the vertical asymptote. Okay, that's for the vertical asymptote. Just a little tip there that you can also find out. So the x-intercept, it does cross the x-axis. So it does cross it somewhere. In order to do that, we need to set y equal to 0. So we can do that since we already solved here. So let's set y equal to 0. So we have, let's do that over here. So remember our original thing that we solved was this, 1/2 to the y minus 4. So we're going to set y equal to 0. So that's going to be 1/2 to the negative 4th minus 1. Alright, and you do that on the calculator. This will flip, becomes 2 to the 4th. 2 to the 4th is 16. 16 minus 1 is 15. So the x-intercept is x equals 15. You know, which I'm a little bit off here. You know that it'll continue and it'll go so slow, it'll cross at 15 somewhere. Alright, so, and then the y-intercept, there is a y-intercept here. It's at 0, 4. That's where it crosses the y-axis. So y equals 4. Crosses the y-axis here if you want to take a look at that. The domain is all numbers from negative 1 to infinity. So remember, you cannot cross the blue, so you can only go from that blue to the right. And those are my x values. So my x values are negative 1 to infinity. Intervals of increase or decreasing. This guy is decreasing from negative 1 to infinity. Decreasing everywhere. Decreasing, like, it's decreasing everywhere from negative 1 to infinity. And then the range, we have all real numbers for the range, all negative numbers, all positive numbers. This will eventually cross and continue into the negatives. Alright, end behavior, we actually won't look too much into end behavior in the lesson. I know I did it in the previous example, but I'm not going to focus on end behavior for these guys as much, but I will write it down just for the sake of completion. I will actually write it down. Alright, so as x approaches infinity, so as x goes to the right, y goes down, which is negative infinity. as x goes to the left, the only way it can go to the left is if it hits -1. So it's approaching -1. Then y is actually going up to positive infinity. All right, so I will do this in class most likely, and I will, do it here in the video, but I probably won't ask you an end behavior question with logs, only with exponential. All right, so just keep that in mind. All right, let's do another graph. Again, graphing takes practice, like finding the numbers takes practice. And keep in mind that you can also use a calculator to help you graph this. You can plug in a lot of numbers for x and get numbers for y. But what I'm trying to do is I'm trying to help you understand how you get certain numbers so that it works out so that you get nice numbers every time, for the most part. So this is why I'm showing you this sort of longer way. Okay, so let's convert this to an exponential function. So I'm going to rewrite it over here. Okay, so we're going to add 2 to both sides to get rid of it, because we're solving for x here. So we have y plus 2 equals ln x minus 1. ln, remember, ln has an invisible e down here. It's log base e, so I'm going to raise both sides to the e so I can cancel. So now I have e to the y plus 2 equals x minus 1. Then I'll add the 1 to both sides, and I'll get my my x equals. So I have x equals e to the y plus 2 plus 1. Okay, so I'm going to choose some nice values for y. So I'm going to set that exponent y plus 2, this exponent right here, I'm going to set that equal to -2, -1, 0, 1, and 2. All right. So if I do that, let me. So y plus 2 equals -2, y plus 2 equals -1. So I'm going to subtract 2 on both sides. So y equals -4. Subtract 2 on both sides, y equals -3. So now we know there's a pattern. It goes by ones and negative ones. So you're adding 1 every time. Alright, so now what we're going to do is we're going to plug this in. So we have x equals, so we're going to plug in -4 for y, and that will give me -4 plus 2 plus 1, which is e to the -2 plus 1. Alright, and then you can plug that into the calculator and get those numbers. Alright, so I'm going to go ahead and plug those numbers in onto the calculator, and I will be back. Alright, so I went ahead and plugged into the calculator to those numbers, and I got those numbers. So again, how did I get the 1.36? I plugged in y equals -3, so I had e to the -3 plus 2 plus 1 equals e to the -1 plus 1, and I kept doing it for -2, -1, 0, 1, and 2 for e, the powers of e. And I got those numbers, right? So I just plugged in for y into, to there. Alright, so now we can quickly graph it. So when when x is 1.14, y is -4. When x is 1.36, so when x is 1.36, y is -3. Let me erase the y is -3. Around there. This should say 2, guys. I'm sorry, it looks like a 1. It should say 2. So when x is 2, y is -2. When x is 3.718, y is -1. When x is a little bit over 8, y is 0. Alright, so we can try to graph that. So it's increasing, looks like it's increasing, and looks like it's trying to approach here. So it looks like it's trying to approach there. So that looks like my vertical asymptote. So we have vertical asymptote at x equals 1, which you can kind of tell from here. When x is 1, that makes that 0, which that's our vertical asymptote. Alright, so that means my x-intercept, we know what our x-intercept is. It's actually here. That's when y is 0. So our x-intercept is x equals 8.389, which that's where it crosses here. The y-intercept is, it doesn't cross the y-axis at all. It actually never even crosses the blue line, so it doesn't cross the y-axis. So there's none. Any asymptotes? Well, we just said that we have a vertical asymptote at x equals 1. Domain, this is valid only to the right of the blue line, right? So for the x values. So when x is from 1 to infinity. Intervals of increase and decrease, this is increasing from x equals 1 to infinity. The range, well, it's increasing everywhere. It's increasing from negative infinity to positive infinity. The end behavior, again, we won't stress this as much on the test. We won't stress this on the test or the quiz, but we will demonstrate it here. So as x goes to the right, the function grows. As x approaches the vertical asymptote of 1, y is going down to negative infinity. Alright, and that's it for the video, guys. I know it can be, this is a completely new, concept, but it's kind of tied in with exponential functions because they're inverses. So the main idea is that you know that they're inverses of each other, you know how to convert between log and exponential, and you essentially know how to plug things into the calculator to get the values for e and log and all that stuff so that you can graph it and know the characteristics. Okay, there's a lot going on in this, so again, you got to practice this stuff in order to hone the skill. All right, guys, take care. Have a good day.